Okay, how are you guys doing? Good? Doing okay? We took a look at the homework assignment posted there. Okay. Let me, I just want to say a quick thing about the homework, and I don't want, I want to avoid problems when it comes to like grading the homework, okay? So you are submitting an HTML file. You're going to download the R Markdown file, you're going to edit it, you're going to update it with your code, and then you're going to knit it into an HTML file, and you're going to submit the HTML file. Now, here's the important thing. There's like over 80 of you, okay? And there's only one grader, and this grader has to grade everybody's stuff, which means the grader can only spend, 5 minutes per person, maybe 10 minutes. Otherwise, it becomes, like a 12 over, even 10 minutes with 80 people, that's 800 minutes. That's like 13 hours, okay? That's a long time to be spending just grading homework, okay? It's very painful, and so the grader doesn't have time to try to go through and understand exactly what you're doing in each little section, right? It takes you a few hours to finish your homework. The grader doesn't have that luxury. The grader has to kind of just take a quick glimpse at what you've done, take a look at what you've output, and make a decision, okay? So you want to make sure your output is as clear as possible to show that you did what the homework was asking you to do, okay? So here I have two examples. I just have, let's say the problem said produce a vector of the first 10 numbers in the Fibonacci sequence. Technically, this answer is correct, but if you just look at this, can you tell that this even works? Like, well, maybe because it's so simple you can kind of get it, but this, it takes a lot longer to kind of look at this and make sure it works rather than something like this where you print out the result. The only difference between this entry and this entry is that this one says print X, okay? And print X produces this sequence of numbers, and now that makes it a lot easier to say, okay, this is the result I'm looking for, right? So if you turn in this where you don't print out the results, okay, you're gonna lose points, okay? Because we've got to, we only have a few seconds to try to decide whether you did this correctly or not, and maybe you did this correctly, but we can't see the results, okay? So make sure that you are producing the results and printing that and including that in your thing so that you get the points that you deserve, right? And this applies outside of the classroom, okay? If in business, okay, if you're trying to sell something to a customer, okay, the customer doesn't want to just hear like, oh, and it's going to work this way and it's going to be awesome, okay? They're unlikely to spend, a bunch of money if you just describe it, okay? But if you have a working demo and say like, hey, this is actually, you can actually see it work here, it's they're much more likely, right? If you're trying to sell vacuums and you just say, our vacuum's really good, believe me, they're not going to buy, right? But if you actually have a demo vacuum, then more likely to make the sale. Okay, let's take a look here, and so homework 1 will be due next week, okay, Tuesday. And then I've already posted homework 2, okay, just so you can kind of get a head start. There's only 6 weeks, and so I'm trying to find the right amount of homework to assign, okay? I'm reducing in my opinion, I'm reducing the difficulty of the homework from the normal 10-week quarter, okay? So, but, I'll hear your feedback, and if you feel like it's still too hard, we'll try to work something out. But as it is, I feel like I'm going to reduce the homework difficulty a tiny bit. Okay, today we're going to talk about programming in R, flow control, and writing functions. Those are very important, and so we're moving right along. Last on Tuesday I introduced this topic of subsetting, and we only got into it a little bit. We didn't get into all the details and examples because we're running out of time. But so make sure you go through and you read Hadley Wickham's textbook, Advanced R, on the sections on subsetting. Take a look at the lecture notes that I've posted and go through that. You guys are all able to download and view and render and test out the code, right? I've posted today's lecture, the RMD file, and you can download that and kind of follow along with the code on your own computer if you want to. Okay, let's start off with the basics. You want to make sure you got your working directory, because if you ever make calls to other files, the place R search will search is your working directory. Okay, and you can do it using set work directory, set WD. This is to set your working directory. Oftentimes, when I'm dealing with a script in R, okay, I would save this script somewhere. Okay. So if I save it to my desktop, this could just be script here. And then a quick thing I do is I go to session and I go to set working directory and I just do to source file location. Okay, and that often makes it easy. Okay, to just set your work directory in the source file location. If you want to hard code it into your script, okay, you just type in set work directory. And then you say, or something like that, okay? And that will make sure that every time the script runs, it's in the correct working directory, okay? If you ever run code and it says like file whatever not found, probably you don't have your working directory set up correctly. Okay, comments, I think you guys already know this, but comments are very useful, and you just use the little hash symbol, okay? In R, let's say you have, if you want to comment something out, you can hit Control-Shift-C or Command-Shift-C, and that toggles whether the line is a comment or not. It's you can just comment entire chunks of code. I mean, you can also do you can type in the hash mark yourself, but you can also turn it on and off using Control or Command-Shift-C in RStudio. So it's a nice little feature there. Okay, it's often a good idea to clear your environment every time. One recommendation is I never save my environment in R. Okay. And I think that's good habits, and that is so it says save workspace to R data on exit. Just set that to never, okay? and then that will never save your workspace, okay? And so get in the habit of unless you're working on some kind of big project where it takes like a long time to load your files into the workspace. But that's not going to be the case in most situations, and so just clear those out. And if you have results that you want to save, you can always save those files and then load those back in. Okay, but as you're working, if you get junk into your data set and you want to clear it out, you can just do you can remove the objects. Okay, you can manually, or you can do list is equal to listing them off, okay? Remove list equals ls. What ls does is it gives a character vector of all the entries in your workspace, okay? And so ls lists these off as you've got I and x, and then here we're saying remove, and the list is basically I and x, and that will remove everything. That's basically what we're doing when you say rm list equals ls, okay? And then it says, oh, you've got nothing, right? Character vector of length 0. So you guys figured out what length 0 vectors are? Difference between that and null and NA. It's part of your homework. Okay, writing scripts in RStudio. I would say this is probably the best way to get your stuff working in R. And is you create a script and then you run them. Okay. Yes, you can run code directly from an R Markdown file. Okay. And in an R Markdown file, you have your code chunk, and then you hit the little play button, and then it runs your code there. Okay. I generally would say write your code in an R script, and then when you're happy with your R script, move it over to the R Markdown file. And then if you do still need to make changes to your R Markdown file, you can do it there. But it's because sometimes the behavior of the code in the Markdown file is a tiny bit different. Okay. I shouldn't say that. The R Markdown code, R runs the code the same everywhere, but I would say with larger scripts, it's easier to work in the script file and then click run. Okay, and then this way you can hit kind of Control Enter or Command Enter to run each line of code. Whereas in the R Markdown, I would recommend against using Control or Command Enter for line entry codes, but rather hitting the play button for each code chunk. Okay. Okay, so pretty much whenever we write code, we control our thing using using conditionals. Okay, and so here we've got basically we've got true and false, right? We've got logical vectors, and then sometimes we want to combine these things, and we've got or vertical bar here, the ampersand for and then we've got exclamation for not, right? And then we've got double or and double and. This is the singularized ones. The exclusive or, and then is true. Okay. So these are for and these are for or, right? Logical and logical or. The single ones are vectorized, and so you can give it a vector of logical values, trues and falses, whereas the doubles will only do the first element in a vector. Okay, and in those cases, the function if, right? So when you do programming, you often ask like if a is equal to 10, right? You got a single true there, or maybe you want something like if a is equal to 10 or if b is equal to 7, then do this code, right? What you want to do in that case, you want to make sure you're only providing the if a single true or false value. Okay, if can't handle multiple, like a bunch of trues or falses. Okay, and so the double and or the double or forces it to only be one true or false. Okay, so here's a little example. I've got x, which is true, true, false, false, and y, which is false, true, false, true. So if I do the or, anytime there's a true, it's going to return true. So the only time that's false is when both are false. Okay, whereas the double or only does the first entry. True, false is true. Okay. The single and returns true only when both are true. That's this one. And then the double and will only evaluate the first true or the first false in each x and y. Okay, exclusive or, this is one or the other, but not both. Okay, so in English, the word or is ambiguous, right? I could say, do you like chocolate or vanilla ice cream? And your answer there is yes. Maybe it's no. lactose intolerant or something. But I could ask the same question, you know, do you like chocolate or vanilla ice cream? And then suddenly your answer is now, I like chocolate ice cream, or I like vanilla ice cream, or something like that. That's the exclusive or, where you have one or the other, but you're not supposed to answer with both. So that's exclusive or. Okay. And then is true will return true only if the element being evaluated is the logical value true with no other attributes. Okay. Otherwise, like the logical value true, you know, it can be coerced into other things and things like that, right? So, because we can ask, oops, true equals 1. So this is going to return true, right? So is this what we want? Maybe, maybe not, right? Is true will only return true if this is the case, and it will not return true here, okay? So there are some times where you want true but not 1, yeah, okay? And so you can't just do a test like this. So that's where you use is true. Okay, we got comparison statements, greater than, less than, things like that, okay? These are all vectorized, meaning that you can give it, x can be, you know, 1 through 10, and y can be, right, so here I've got x and here I've got y, and I can say is x less than y, and it will compare them element by element. It goes 1 versus 4, 2 versus 6, 3 versus 8, 4 versus 2, false, things like that, okay? So this comparison is element-wise comparison there. Okay, and then you know, there's percent in percent, which is a handy thing for the you can say is 11% in percent y, and that's false, but is 5 yes, 5.5 no. Okay, so it just kind of does this quick search in the other thing, and you can even do x in y. It's going to search for each of these things in y. Okay. All right. So we have these ways to combine and test logical statements, and now we can control the way our program flows using these control statements. So if is probably the most common one, okay? And it's going to expect a length 1 logical vector, right? So you're either going to give it a true or you're going to give it a false. And conditions of length greater than 1 are accepted with a warning, but only the first element will be used, okay? And then other types are coerced to logical if possible. Okay, and then curly braces are used to group the expression that will run if the condition inside the if statement is true. And if there's only one expression to execute, the curly braces are optional. All right, so let's look at this. Okay, so we say x is the vector 1 and 3. Is 1 in x? Yes. Okay, and we're going to say if 1 is in x, print hello. All right. Because there's only one statement here, I left off the curly braces. Otherwise, I would put a curly brace up here and a curly brace afterwards to say run all of these code, all the commands inside the kind of the if chunk there. Okay, and so here it says because this is true, if this is true, which it is, print out hello. That's how it does. Okay, we can ask, is x greater than or equal to 2? okay? So what this returns is this returns a logical vector of length 2 where the first element is false and the second element is true, right? So if I stick this inside my if statement, what is it going to do? It'll accept it. It's not going to error out, but it produces a warning, and it says, you know, the thing that you put in this conditional, it had a length longer than 1, okay? And so ours complains, but it runs the code, okay? And whoops. And because it ran the code, what's the output? Well, it's only going to look at the first element, which is false, which means don't run this, right? So it evaluates this, but it's not going to run this part because this part evaluated to false. So if we wanted to work at this, we can do any, okay? Do you guys know any, what any does? Any is like the super OR, okay? So if anything, right, you have a logical vector with a bunch of falses and trues or whatever, okay? If any of those are true, then the whole thing evaluates to true, right? It's like just having a whole bunch of OR gates. And so if any one of those are true, then it will evaluate to true. Otherwise, it will be false, right? So it's only false if every single one is false, okay? So here, any here becomes true. And then when we run this, this is a single true value, and that will get evaluated then, okay? All right, does this all make sense? So, you know, you just want to, when you're writing your code, don't do stuff like this, okay? Don't put in a logical vector longer than length 1. Okay, it's not a good idea. Okay, and then if we want to make our life more complicated, which we probably need to do, okay? You can use else statements, right? So if this thing is true, then do this. If it's not true, then do this other thing, okay? And so you've got else, and then, you know, you can also have another switch, right? So you can have if this is, you know, if x is less than 0, it's negative. If x is greater than 0, it's positive. And else, meaning this is not the case and this is not the case, then it has to be 0, okay? If it's neither less than 0 nor greater than 0, it must be 0, right? And so if we run 3 through the thing, it evaluates, this gets evaluated to true, these don't get bothered to evaluate it, okay? And it's going to print out positive here, okay? If you're going to use else, you've got to put it on the line with the closing curly brace, okay? Otherwise, if I had the else on the line below, it's not going to associate the else with the previous if statement. Okay, so you've got to put the else on the same line as the closing curly brace. Where's my? Okay, yeah, it's not working. Okay, and then so in this case, I run through, I say x is equal to 0. So this is false. So it's going to evaluate this one. This is false. So it evaluates this one, and it says 0. Okay. In this case, I've got if x is equal to 3. Okay, here I have if x is greater than 0, print positive, and then I got else if x is greater than 1, print bigger than 1. Okay. But this thing doesn't even get evaluated because this first if is true. So this doesn't get evaluated, right? Because the else's will only get triggered if the first thing is evaluated as false. Does that make sense? Okay. So those are your if statements. Okay. We can talk about loops, all right? With loops, the kind of the simplest type is the for loop, okay? And you give it a vector, and you say for each element in the vector, okay? Our most common vector that we give it is going to be the integers, right? So oftentimes we just say 1 through 10, okay? And these integers are often associated with indices or something like that, okay? So we say, you know, for x in 1 through 10, and so what this is going to do is it's going to run this code right here, and the first time it runs through, it's going to say x is 1. It evaluates this code. X squared would be 1 squared. And then it prints that. Cat is just a way to output things onto the screen. Okay. Then it finishes running this code. Then it says, okay, let's go back to the top of the loop. Now let's go to the next thing in the vector. The next thing in the vector is the number 2. So it squares the number 2 and it prints out 4. Okay. And then it goes on and says that what's the next element in the vector? 3. 3 squared is 9, and it prints that, and it puts that there, okay? Or it cats that, I should say. Why am I not able to open this? Let's get here. Okay, what would happen, just a quick question, if instead of cat I used print, what will it output? So here, if I run this, I get 149, 1625, okay? What if instead of cat, I put in print? Same thing? Different? No response. What's that? It puts 1 per line. And then it outputs them as, you're going to get that bracket 1 to kind of indicate that it's a result. So you get this, okay? 1 per line, and then you get kind of the bracket 1 to indicate this is a vectorized result. Whereas cat is just outputs to the screen, okay? What happens if I have both of these activated? So it outputs to the screen, then it runs the print command, okay? And then it print automatically includes the end line character, and so then it outputs to the screen, and it does this, right? So this is probably not what you wanted, okay? And if I get rid of this space thing here, and it just prints this out. Okay, anyway. So take a look at this. So we're often used to providing the vector of integers, right? We often say like 1 through 10 or 1 through 100 or 1 through 5,000 or something like that. That's probably the most common scenario that you did in Stats 20. Okay, right? You've done this, yes? Okay. But you can also provide it vectors or lists that are not your normal vector, right? So here I've got the list 1:3, letters 1 through 7, true, comma, false. Okay, so let me see, print this out here. Okay, so here is list L, and if I say structure of L, this is what I have. I've got a list of 3, an integer vector, character vector, and a logical vector. Okay, that's my list L. And now I'm giving it a for loop, and I'm saying for y in L, and what are we catting? We're catting length of y. So what is this going to output onto the screen? Any ideas? What? It's going to output 372, okay? Because it's iterating through each thing in that list, right? So imagine a train. I've got 3 train cars. Inside the first train car, I've got a vector of 3 letters, right? Or three integers, okay? And then in the second train car, I've got a vector of 7 letters. And in the third train car, I've got a vector of 2 logical values, okay? So it goes to the first element in the list, and it says, how long is the thing inside this train car? It's 3 long. And then it goes to the next one. How long is the thing inside this train car? It's 7 long. And how long is the thing in this last train car? It's 2. Okay? So this is probably not your traditional. I think most of the times when we look at for loops, we're accustomed to saying for I in 1 through 100 or something like that. But it doesn't have to be that way. It can be, you can give it a vector or a list, and it's going to go through each thing, and it's going to run the code for that thing, right? And so it says for y and L, so in the first iteration, y is the vector 1 through 3. In the second iteration, y is the character vector of the letters 1 through 7. And in the third iteration, y itself is this logical vector of true, false. Okay, and so it outputs 372. So here's a question. What if I write this for loop? Let's say x is 1, 2, 3. Okay, and I say for I in x, and I say length x. What is it going to print out? Well, first of all, what does length produce? Here, we'll okay. So length of x tells you how many elements are in that vector, right? I got 5 elements in the vector. That's what we have, okay? So if I do for I in 1 through x, length of x, what's this going to produce? What do you think? Do you think it's going to give us, what, 3, 3, 5, 4, 4? No, it's not going to do that, right? Well, we'll run it. It's going to produce a bunch of 1s. Oops. Let's do print length x. Okay. I'm sorry. It just prints the or not length of x. Sorry, length of I. You're going to produce just a bunch of 1s here. Okay, because the first time it runs through, it's looking. I is just. This will make more sense, I think, if I say print I. Okay, I is just a character vector of length 1 with the contents 1. And so if I say, what's the length of that thing? It's only 1. Okay, the second time it runs through, I is the character vector with a length of 1 containing the word 2. What's the length of that thing? It's just 1. Okay. If I wanted the number of letters, I could use n character for this. And then I think this is what we have in mind. So I, the first time, is the word characters O-N-E, and there's 3 characters, and there we have that. Okay. So sometimes when you're writing code, you're not keeping in, you forget that each iteration, you're getting a different thing in the vector that you gave it, okay? But, I don't know, probably your loops, your for loops often just use this 1 through 10 or something like that. Okay. Now this should have gone. Sorry, this is out of place in the notes here. I'll fix it. Another useful conditional is the if-else. Okay, and it basically compresses something like this. If this is this into this, you give it the conditional here, value if it's true and value if it's false. Okay, that should have gone before the loop section here. Okay. Oftentimes when we run our loop, we want to store the results of our loop somewhere. Okay, and so in general, it's best to tell it where you're going to store the results and then store those results in that place where you said you're going to store it. Okay, so so here I'm creating a results vector results, which I repeated the value NA 10 times, or whatever value you want to put there, and then but probably NA makes sense, just in case you don't fill it out, you don't have the zeros throwing off the mean or the median or whatever summary thing you're doing here. Okay, and then we're going to just replace, we're going to index subset results into index X and store the result there, right? So here the results is a vector of 10. The first time we run it, it takes 1, it squares it, and it stores the result of 1 squared into position 1, right? Because X is 1 the first time, and then so on and so forth. Okay, I think this is simple enough. You guys understand this line of code here? Okay. This is bad, okay, in that here I start off with an empty vector, right? And then I say, okay, what we're going to do is we're going to combine my empty vector with the first entry, and then now my vector results has 1 entry in it, and then we're going to combine the current results with another thing, and then we just keep growing the vector that way. Okay, it's probably not the best way. I mean, with 1 through 10, it's going to make very little difference, but with a billion results or something, it's going to take more time. Okay, and also bad is here I gave it a place to store it, and I'm saying store it in position 1 or position 2 or whatever. It's not as bad as this, but every time I run it, I have to resize my results vector, right? Because the first time I run it, the results vector is only length 1, and then the next time I got to resize it and say, oh, extend it, put a at another spot for it. Okay, all of these things work, but if you're doing things with 10,000 or 1,000,000 iterations, sometimes they can make a difference in the computational efficiency. We've got other types of loops. We've got the while loop, okay? And the while is going to run everything in the code until this statement is false, okay? Until this thing fails and is false. And so your while loop can get stuck in an infinite loop, right? With the for loop, there's always an end, because you're going to say do it for 1 through 10 or 1 through 5,000, or you're going to give it some kind of vector with a finite end. You can't give, a for loop cannot go infinite because you can't provide it an infinite vector, okay? Whereas a while loop, it's going to keep running until a condition is met, or I'm sorry, until the condition is not met, and then it boots out. So if the condition is always true, the while loop is always going to run. Okay, and if you get stuck in an infinite loop, so if I do something like while true, so this whatever I write here, this is this is always going to run, right? And so this is going to, so it's like going forever. There's no stopping it now. Okay, so you get this little, there's a little stop sign here that says like, oh, I made a mistake. Save yourself. Okay. So you know. So don't put something here that's going to evaluate true all the time, right? So we have that. Okay. And then on the other hand, we have the repeat loop. Okay. And the repeat loop is always okay. If you just do this, it's also going to do its own thing. Okay, and it's just going to go on forever. Okay. The way you save yourself with the repeat loop is somewhere inside the loop you need to have a break statement, okay? And the break statement is what kicks out of the repeat loop, okay? And so generally you would have some kind of conditional inside the repeat loop, and then when this condition is met, then it's going to break and kick out. Okay? So you got the while and the repeat loop. They're fine. Okay. We've got break and we have next. Okay. So what break does is it's going to end the current loop. Okay. As soon as it evaluates break, it kicks out. Okay. So in this case, if I say we're going to give it the vector 1 through 10, and we say for I in 1 through 10, you know, just print out I. And what do I have here? I've got if I mod 2 is equal to 0, meaning if I is an even number, break. So it runs the first time, it prints a 1. The second time, I've got I is 2. Then this gets evaluated. It says, oh, this is true, and so I'm going to break, and then it quits, and we're done. Okay. If instead of break, I used next, what it does is it runs. It says, okay, number I is 1. That's not divisible by 2, so we're going to keep going. Print it out. Okay. Then we go into the next one. I is now 2. It looks at this. It says, oh, I is divisible by 2. That's true. So evaluate this thing. Next. Okay. And so as soon as it hits next, it's going to skip everything else left in the code and go back to the top and say, okay, we're going on to our next entry. I is now 3. And then we go through it. And then now we just get our odd numbers here. Okay. Okay. As far as the for loops, we often have, we want to do things, and so we can do probably the most common thing is to do just like for I and 1 through 3 or something. But if we wanted to give it something like L, okay, so here L is this list, right? And if I ask structure of list, I can do this, right? Sequence along, and if you give it something, what it does is it basically just produces a vector that counts 1, 2, 3 up to the length of whatever it is that we're looking at, right? So x is this. If I say sequence along x, what's it going to produce? The integers 1 through 5, right? So sequence along is pretty much the same as doing 1 through length of L, or sequence along, or you can say create a sequence of length 3. Okay, so these are all kind of equivalent ways. I think you know, when I coded, this is probably the most common thing I do, is to do 1 through length of x or something like that. But sequence along works just as well. Okay, all of these things so far probably can just be done using subsetting or using the apply command or things like that. Loops, especially in R, loops are not super efficient, but they're often easy for us to understand, okay? And so as you're coding, if you want to start off with a loop, that's fine. And once you get it working, then you can think about, can I vectorize this, right? Because if you vectorize things, it's a lot faster. So if I just do, if I wanted 1 through 10 squared, this is probably the fastest way to do it, okay? Just to square your vector rather than having to write some kind of for loop. And then, you know, just computationally, this is also much more efficient than trying to do it. But it works with the for loop and whatnot. Okay, so you can start off with loops and worry about efficiency later, and that's my recommendation always. Always start with coding that is correct, then work on making your code more efficient. Okay, I want to talk about functions. Okay, functions in R have the form this, right? You have the name of your function, and then you're going to say this thing is a function, and the function receives arguments 1, 2, etc., etc. It runs some code, and then it's going to return some kind of output object. Okay, and so you know you give it variables in arguments, you evaluate stuff, and it gets spit out. That's your function. Okay, so pretty much any function that you have here, we can ask about. We can have it run. So if y is a vector 1 through 5, okay, I can say calculate the standard deviation of y, and it outputs it, okay? And if I look at the code inside standard deviation, we see, oh, this is a function where it's going to receive 2 arguments. X is some kind of vector, and another argument called na.rm if it needs to remove values that are false, okay? And what is it going to return? It's going to return the square root, which is a function itself, of the variance, which is another function, and then here's this thing, which basically just says, make sure everything is treated as a type double, numbers, okay? And remove things if you need to, okay? Remove NAs. And then other things, you know, if I say, what is the square root thing? It says, oh, this is a primitive function. So we don't actually, it doesn't show us the computations inside how the square root function is working. But it's also a function, okay? Okay, and if the function has only one line, the curly braces can be left off. And if the function return is not used, then the value is the last expression in the function. Okay, so the last thing that gets evaluated is there. So here, f, the functions themselves are also objects, which means we can treat them like any other object, right? So here I'm writing f is a function of x, where I do x times x, right? So f is a function of x, and what's it going to do? We're doing x times x. So this is basically a squaring function. So if I say f of 9, it's going to return 81 down here, okay? Or if I give it a vector, 1 through 10, okay? Y is 1 through 10, and I say, give me f of y. It just squares everything in it, and it returns that. Okay, no problem there. Okay, the function f itself is an object, so I can throw it into a list. I can say, what is the list with f? Then it puts it in there. Okay. If I say, what is the type of f? Then it says it's a closure. So this is a little bit different from our normal data types of integers and doubles and things like that. The function is a closure, which is kind of a special term that R uses, but it basically allows you to throw functions into other functions, right? You can have functions of functions. Okay. Oh yeah. So here, this is a function where what it returns is another function. Okay. What is this? All right. So here. Let me just copy this. And I'll just try to explain what's happening here. Everybody gets. Okay, so f2 is a function. So f2 is this, right? So if I say f2 of 1, it returns back a function. And then if I say f2 1, 1, now it adds these two together. So what is this doing? It's basically returning okay, so what f2 returns, when I first run it, it's going to return a function where it's now a function of y, okay? So I can call this the add 10 function. Add 10, f2, if I do this, okay? And then, so now if I say, what is add 10? It's this thing, but if I say, okay, add 10 of 9, then it adds those two things together, okay? And I can say add 10 to 90, and it gives me back that. I can create a new function using f2, and we're going to call this add 100, okay? And the result is f2 of 100 produces a new function, right? So we can see these new functions appear over here, where add 10 is a new function and add 100 is a new function of y. So I could say, okay, add 100, that's a new function. Okay, and what is the contents? This is how it's running, and add 100 to 40, and it's basically doing that. Okay, so we can have a function that is returning other functions. So f2 is the function maker, and if I say f2 of 100, it produces a function where its sole purpose is to add 100, and things like that. Okay, these are just silly examples here, but they can be expanded into kind of more complex things. Okay, we've got return values. Okay, so in these cases, we had a lot of implicit returns. An explicit return calls this function return. Okay, and it says return this particular thing. If you don't include return, it's just going to do the last function, the last expression that's evaluated. Okay, so these two things are equivalent in that they're both going to return x times x. But this one is explicit because it says that. If you want to return multiple values, you have to group them together in a vector or a list. Okay, you're only allowed one return per function. Okay, so if you want multiple things being sent back, you have to group them all together into a single object, like a list or a vector, and then you return that list or vector. Okay, so even the most complicated things, such as when you run a generalized linear model in R, what it's doing is it's doing a bunch of different things, and then all of those results it groups together into a list, and it returns the list. Okay, because you're only allowed one return in a function. You're only allowed to return one object. Okay, so here if I want to return the value, its square, and its cube, I can group them all together using a vector, and then it's going to return that vector. Okay, or here I'm going to return the list of x, its square, and its cube. And then we can then reference these results as such, the list, right? So if you look at, you know, just like the code for create a linear model, yeah, okay, it doesn't say z, return z, but basically z is the last thing that gets evaluated, so z is the thing that's being returned. And what is z? If we look at all the code inside that gets run when you run linear model, okay, so when you run linear model, it's running a function, and we can see that z is a list. So here's z is a list where one of the things in the list is the coefficients, another thing is the residuals, another thing is fitted values, weights, rank, degrees of freedoms on the residuals, and things like that. And then if it has additional things, then you know, it stores these and says, you know, throw in offset and all of this. And so, you know, if I say x is 1 through 100 and y is our norm 100, and I say I want the results of a linear model between y as explained by x, okay, we can see that results, oops, the structure of results is a list of 12 things, okay, and that's what is being returned here, okay. When you run linear model, it's returning just a z. Z is all of these things. This is the list that is being produced, and then all of this stuff gets thrown in here. Okay, so you can create functions and it'll do that, and then, you know, here's the thing. Okay, with argument names, okay, when defining a function, we are also implicitly defining names for the arguments when calling the function, okay. And so when we create a function, here I'm calling it a function where it takes 3 arguments, x, y, and z. And basically it's just going to print out x is x, y is y, and z is z. Okay? So if I say run the function 1, 2, 3, it prints this out. And basically it just means the first argument that comes in is called x, and therefore in the code that I evaluate in that function, basically that first thing that comes in is going to be referenced whenever I use the letter x here. Okay, and thus when we run the code, okay, when we call the function, if I don't specify the letters, it's going to expect them in this order, x, y, and z. Okay, but because I've named them x, y, and z, I can also say I want z here, z to be 1, x to be 2, and y to be 3, and then the function assigns them accordingly, and it will say, okay, x is 2, y is 3, and z is 1. Okay, and then if you only explicitly mention one of them, in this case I say y is 2, then it will put the other things into their respective positions. Okay, it says, okay, well the first thing that's left over is 1, and then the next thing that came is 3, and because y has already been mentioned, then we're going to throw that into the z position, and then it goes there. Okay, and it will it complains though, so if you give it more than the number of arguments that it wants, right? So here's my function, f is this function, okay? And if I say f and I give it 1 through 3, whoops, 1, 2, and 3, that works fine. But if I say 1, 2, 3, 4, it says I don't know what to do with this thing, and it kicks back an error. Okay, and if I don't give it enough, it's going to say I don't have the thing z, and I've got no default value for z, so I can't evaluate this either. Okay, so that's what we have, right? So we've got this, and you can give it default value so that if it's not specified, then it will still run. Okay, so in this case, I give it some default values in the function definition here. I say if you're not given, so compare it to here where I didn't give any default values. Over here I say, you know, if you're not given anything, then just use these things, and it does, okay? And if I give it one thing, then it's going to plug it into X and use the default values for the others. And if I give it Z, then it plugs that in accordingly and gives default values to the others. There's an important thing called scope in R, okay? And what scope means is that if you write your function in a sloppy form and it can't find the thing that it's looking for inside the function itself, it's going to search a higher scope, okay? So scopes are like little sandboxes or environments where these values exist, and then they're combined and evaluated, okay? And then maybe inside the function, so here I've defined f as a function of x, okay? Inside the definition of the function, I don't mention y at all. And the function is supposed to take x and it's supposed to add y, okay? So when you run this and I say, here's a function and I'm providing it the argument 3 here, it's going to plug in, it's going to say, okay, I've got x, x is 3, and I want to return the value 3 plus y, okay? R is very generous, and it says, oh, I have no idea what you're talking about when you say y, okay? Because that's not defined in my function space. So, okay, I'm going to peek out of my world, look around, oh, look, y is right here, it's called 1, I'm going to grab that, and I'm going to use it here, okay? And so it says, okay, 3 plus 1 is 4, ta-da, here's your answer, okay? In general, this is sloppy function writing, okay? When you write your functions, everything you're going to use in the function should exist in the function. You don't want to have a situation where R is having to go outside of its normal scope and look around. However, maybe you're kind of lazy and you don't feel like having to redefine everything in the function. R is, you know, is friendly towards that, and it'll allow you to do this, okay? But what happens, so look at this. Here I have pretty much the same function. G is a function of x. Inside the function, I define y as 2, and x plus y is what we're going to return. So I run G is 3, it adds x and y, and it returns 5, okay? If I ask what is the value of y at this point, what is the value of y? Is it 2? Is it 1? Yeah, it's one of those values. Okay, here let's run this. Okay, so I'm gonna copy this over into my script, and then I'm gonna just delete everything out so you see that this is in the case. Okay, I've got y is equal to 1. Okay, I've got creating a function called g. All right, g is this function. Y is equal to 2 and x and y. And now I'm going to execute function g using the argument 3. I do that and it returns 5. And then I ask, what is y? Y is still 1. Okay, so because this y equals 2, this only exists inside the little scope or in the environment created by the function. The y that's in here does not affect the y out in the global environment. Okay. So, you know, if I say, you know, g of 1, it's still going to add this y equal to 2. And it doesn't touch the y out here in the global environment. Okay, so this is what this basically says. Variables defined within a scope only exist in that scope and for the duration of that scope, meaning variables inside a function, which creates its own little scope, only exist there and only while that function is running, okay? If the variable exists with the same name outside the scope, like the global environment, they are separate and they do not interact with the variables inside the scope, nor are they overwritten or copied or affected. So you can think of a function as its own separate environment or sandbox, that only communicates to the outside world via the arguments, the stuff that comes in, and the output expression, the stuff, the return function that gets sent out. Okay, so if you execute this command, remove list equals ls, which clears out the workspace, right? Inside a function, which is, terrible idea, by the way, you would only delete the objects that have been defined inside the function. Everything outside of that is unaffected, okay? The only exception is this thing, okay, the super assignment operator, which searches a higher scope or the global environment, okay? So you have something called super assignment, and you can ask for help on assignment operators here. Okay, and you have the regular assignment and then super assignment. Okay, these things search the parent environment. So if here here if this is the regular old assignment, g of 3 gives me 5, right? Y is still 1. Okay, but if I did this super assignment, okay, y is still 1, but now if as soon as I run this function, g of 3, y has now changed to 2. Okay, so this thing, when I run this code, the super assignment goes to the higher environment and changes that value. Okay, there are times when you might want to use it. Okay, but in most cases it's a dangerous thing to do. Okay, and I recommend against it. I'm almost hesitant to put this in my notes here because some students will say, oh, this is the solution to the problem I'm trying to figure out. I'm going to do this thing and go on it. Chances are 99% of the time your solution can be achieved without using this global assignment operator, okay? So don't, I recommend against using it, okay? Try to think hard and think creatively and carefully and try to come up with an idea that does not use this thing, okay? It's like, I don't know, I feel like I'm showing you how to use a gun here or something, okay? Generally not a good idea here. Okay. So here I've got x, y, and z. They're all the value 1, okay? And f is a function. Inside f, I run another function. And inside of each of these things, I got y is 2, z is 3, and we're going to return the sum of x, y, and z. Okay, and so I say return g. Okay, and when we do that, this is the last thing that's evaluated, right? So I run f, it goes inside, it runs, it does y, and then it looks at the last thing, it says run g. Okay, well g is then going to say, okay, well I got to look at this function, and inside there I'm going to define z as 3, and we're going to return this value x, y, and z added together. So when we do that, we get 6. Okay, whereas but in the global environment, x, y, and z are unaffected. Let me ask you another question. So let's clear this out. Okay, I got x, y, z, and f, and this is my function. Okay, prior to doing return g, let's say I say print x, y, z. What's it going to print? One, two, three. 1, 2, 1. Where does the print reside inside this thing? Exactly, 1, 2, 1. Okay, because the print resides inside the scope for f. okay? The G exists, is a scope within inside, okay? And so this Z can't see the Z defined inside of G, okay? This is like if you did this in your code, this is like a terrible idea. You shouldn't do this, okay? But I do this as an example to kind of indicate like what's going. Now, if I put this over here, okay? So I put the print command here, okay? And I run the function, okay? And I run F, what's it gonna do? Is it even gonna print out the thing, or is it just gonna return 6? All right, so it's gonna print it out, and it's gonna print out 1, 2, 3, and it's gonna print out 6 here, okay? Because it's running, it goes and it says, y is 2. Then I want to return G. Oh, okay, I got to run this function. It runs the function. It says Z. I'm going to print this out. I'm going to return this thing. And it gives that. Okay. So scope is a thing that can throw off a lot of students. Okay. So you just want to pay attention and make sure you understand what exists and where it exists. Okay. Here. Same thing, but now we've done the super assignment, okay? Okay, and when we run this, it returns 6, and if we ask back X, Y, and Z, it returns 1, 2, and 3. Because what's happening is when it runs this Y, it searches the higher scope and it goes, oh, okay, I found it here, and it changes it to 2. Over here, it's running G inside the F, okay, but it doesn't find the Z here, okay? It doesn't find the Z inside the F, so it climbs the higher scope and it goes out to here, okay? Now if I modify this a tiny bit, and if I define a Z here, so X, Y, and Z are all 1, and I run this, okay, it returns 6 because it's doing 1, 2, and 3, okay, but what it does is when it climbs the higher scope, it finds the Z here. The Z here gets changed to 3, which keeps this Z out in the global environment safe. And so we see that this remains 1, 2, and 1. You guys, does that make sense? So the super assignment climbs the higher scope. If it finds it there, it's going to assign it there and then stop. Okay? And if it doesn't find it there, it keeps climbing the scopes until it finds it. And so this is like a decoy Z, okay? And it gets killed by the super assignment. And the true Z is, I don't know what I'm talking about, but anyway. So that's what happens there. Okay. When do we use functions? The goal of functions should be to encapsulate a small reusable piece of code. It should be clear what the function does in terms of simple verbs, and so this is kind of like some coding philosophy. And you want to kind of keep things nice and modularized, right? You don't want to do a whole lot of like copy, like you write a big code chunk and then you copy that entire code chunk into somewhere else and do that, okay? Because let's say you realize, oh, I want to modify something over here. Now you've got to find the exact same thing and modify it in multiple locations. So ideally, you want to modularize your stuff so that this thing does one thing, and then if you can create a function for that one piece, and you can reference it in other places, then that's great, because if you realize you made a mistake over here, you fix in one location, and you don't have to copy and paste your changes in all sorts of other locations. That's why we use functions. Okay, infix operators. This is a thing, but yeah, don't worry about it. This is just how, like, when we do plus, right? Like, if I do 3 plus 3, okay, it returns a thing. And it's not that I'm running the function plus on 3, you know. This is technically how the function should be called in R, right? Like, because R, you give it the function name and you give it the arguments. But it would be ridiculous if we had to do math this way, right? We would hate it. So we can just use plus like this, and that's called an infix operator, okay? And it basically allows us to do things like this. Okay, so here's just some tips on writing programs. A lot of times you can save a lot of headaches if you do a little stopping, thinking, and planning, oftentimes with a piece of paper, rather than just starting to type things away on the computer, okay? Maybe if you're really good, you can just start typing away. But a lot of times, a little planning, a little writing things down on a piece of paper is a good idea. So understand the problem, work out a general idea how to solve it. This is the paper part, okay? Then turn it into some kind of code implementation, and then try it out. Okay, and that's how it goes. All right. And then, you know, what you can do is you can often break down a daunting task into a bunch of smaller tasks, and each of those smaller tasks can then further be broken down into operations that can work. Okay. So here's an example. Bubble sort. Have you guys heard of this? This is like a sorting algorithm, and we don't really use it anymore. But back in the day, when memory was like this very limited resource on the computer, bubble sort had its advantages because it only used one little piece of memory here, right? So basically, it sorts a vector of numbers by evaluating consecutive pairs of numbers and swapping them if the former number is greater than the latter. So this is kind of how it works. So here's the list. It compares two numbers and it says, oh, the 8 was bigger than the 4. Okay, so here it goes, okay, starting here, 3 and 5, compares those. It says the 5 is bigger than 3. Now it looks at these two. The 5 is bigger than the 1, so the 5 gets moved over, and it continues on. The 5 is smaller than the 6, so we go on to the next one. 7 is bigger than the 2, so we've got to swap those positions. Moves on. 7 is bigger than the 4, so we swap those positions, and we're done. Okay, and then it just keeps going on and on. So here it says, okay, the 3 is bigger than the 1. 3 is smaller than 5, so leave it. 5 is smaller than 6, so leave it. 6 is bigger than 2, so swap. 6 is bigger than 4, so swap. Okay, and this is how we go about doing the bubble sort, and then it's going to eventually go. Okay, and work this out. So if we had the task of coding this up, how can we do this? All right. So what we want to do is we want to write a function that's going to receive a vector of input values, and then we're going to sort them using the bubble sort algorithm, and then return a sorted vector. Okay, and so here it checks and it says, okay, that's good, okay, and then we're victorious. Okay. So as far as okay, so let's try to code this. Okay. Okay, so maybe I will just shuffle the values 1 through 8. Okay, here actually let's. Okay, so x is this vector 3, 8, 4, 5, 1, 7, 2, 6. Okay, and we want to sort that from least to greatest. Okay, so what we're going to do is we're going to create a function. I'll call this bubble sort. Okay. Okay, and so bubble sort itself is going to be a function, and it's going to receive one argument, x. Okay. Okay, and so the argument it receives, the argument x, is kind of the unsorted numeric vector. So, you know, if you wanted to write good code, you probably should do some checks to make sure that the input is numeric and it's kind of the form that we're expecting. Okay, so let's just talk about how we can go about coding this thing. Okay, so the first thing we're going to do is what we want to do is we want to look at the first pair of numbers. And then we're going to test to see if the left number is larger than the right number. Okay, so left number will be at I, index I, and the right number will be at I plus 1, right? Okay, and if the left number is bigger than the right number, what do we do? We swap them, right? If left is bigger than right, swap. Okay. Otherwise, what do we do? Otherwise, move on to the next pair. Okay. And then you're going to do this for all of the elements in the vector. Okay. And so when we finish that, what will we be guaranteed? We will be guaranteed that the biggest number is all the way to the right. Okay? So the first time we do this, the biggest number will be in the rightmost position. Okay, so the next time we do this, what do we do? We're going to run it until we get to the second to the last position. Okay, so for the second iteration, we do this until we get to the second to last position. And then what do we do for the third iteration? Do until the third to last position, right? Etc. Okay? Until you're done, right? Until the last position is basically just the first two numbers, right? Do until, okay, etc. Do until no more pairs to swap. So, yeah.
Isn't this similar to like Metropolis algorithm?
I would not say so. So this is just you're just comparing to see if one number is bigger than another number. If it is, swap them, okay? And you keep doing this until it gets to the end. It's called the bubble sort because you're basically creating a little bubble of two numbers, and maybe they get swapped, maybe they don't. And this bubble kind of moves down. And it's just to sort a vector of numbers, right? Okay, so how should we do this? Okay, what we're going to do is let's just start off with, I'm going to just start with I equal to 1, okay? and we'll just get the first thing. And we're going to just do if x sub I is greater than x sub I plus 1. This is to see if the left is bigger than the right number, right? So this is what we do. Okay, so if it is, if left is bigger than right, what do? We swap them. Okay, so how can we swap positions x1 and x2, or x1, xi and xi plus 1? Okay, I'm going to create a holding cell, and I'm going to put xi in there. Okay, and then I'm going to put in into the old xi position, I will put xi plus 1, and then into xi plus 1, I'll put in the old xi, right? I have to create this whole thing because if I ran, oh no, see, if I ran this, I would get in trouble, but because as soon as I rewrote this, then if I had just this, which is what I originally wrote, this would not swap, right? This would just overwrite, 3 goes into the first spot, and then now I have a 3 and a 3. So here I have to put in, okay. So are we agreed that this will swap at least the left and right? Okay. So so we can just kind of see if this works here. Okay. So here I have x is this. Well, this is not a good example. Let's just see if I can do. Okay, so y is going to be 5, 4, 3, 2, 1. Okay. So y is this. So if I do bubble sort y and I run that, okay, it worked in that it switched the 5 and the 4. Okay, so that's a good sign, right? So this is what we want to do. Okay, and so what we're going to do is we can say, okay, let's do this for I in, we'll go 1 through, and what we want is the length of the vector minus 1, right? We don't want to go all the way to the end because it goes to I plus 1, right? So we'll just say, I'm going to call j to be the length of the vector, length of x. So we're going to go from I to j minus 1. Is that good? Okay, and then so if I do this, so now I'm going to put this inside this right here. Okay, so what will this do? Bubble sort, this is going to be one iteration, and this will just make sure that at the end of it, the rightmost number is the largest number. Okay, so here is one sorting, right? So if I have x and if I do bubble sort x, it moves, it has successfully shifted everything down so that 8 is now the biggest number. Right? Is that okay? So I've done this part, right? Look at the first pair of numbers, test to see if the left is larger than the right. If so, swap, otherwise move on to the next pair. Do this for all elements in the vector. So I started off at the very beginning, check if the first position is bigger than the next position. If it is, we swap them, otherwise we don't do anything, right? Okay, and we do this for positions 1 through 7 or 1 through length minus 1. Okay, so that's one iteration. Now what do I have to do? So that successfully pushes the 8 all the way to the end. So what do I want to do now? I want to do this again, but this time I only want to go to the 7. right? And I want to do this again, and this time I want to end at the 6, and so on and so forth. So how can I do that? How can I say, so we're gonna put this entire thing into a loop itself, right? We're gonna put this entire thing into a loop, but this loop is gonna start off where basically we want the last position to be 8, and then the next time we want the last position to be 7, and the next time we want the last position to be 6, and so on and so forth until we get to 2, right? Does that make sense? So basically I'm going to build a loop where I'm going to start at the length of the thing, 8, okay? Or yeah, in this case 8, so that first it goes to, and then we're going to count down until we get to 2. So I'm going to build a loop where I'm going from 8 down to 2, okay? So, so how can I do that? Okay, well, what I will do is I'm going to replace this J with I'm going to call this L, okay? And I'm going to do for J in L through 2. So we're counting down from 8 all the way down to 2. 8, 7, 6, 5, 4, 3, 2. Does that make sense? Okay, and then I put that, all of this into a thing there. Did I lose you guys? Yeah, question.
You have to change the J in the second one.
So, well, I changed it here so that, because when I first run this, J is going to be L equal to 8, and then J will then be 7, and then so on and so forth. Okay, so this is now my bubble sort code, and let's see if this works. We'll do bubble sort Y. Yeah, that looks good. Okay, let's look at X here, and we'll do bubble sort X, and that looks pretty good. Did I lose anybody? Are we okay? Basically, I just took this, I wrote this out, right? We said, well, how do we run the code? And we said, okay, we're gonna do it like this, and then the first time we do it, then the second time we keep going that way. And then I put it into code. It's like draw the owl. So if you draw out a sketch of what it is that you're going for, I think it makes it a lot easier in terms of trying to accomplish what you're doing. Okay. Yes, questions?
Would it still work without the upper for loop? Or just take longer because you have to.
Like if I got rid of this one?
Yeah.
So if I got rid of this one, what would happen is we are just doing this part. Look at the first pair of numbers, test to see if the left number is bigger than the right number. If so, swap. If not, move on to the next pair. Okay? And that's what this does. Okay? And if you do that, it will successfully move the biggest number all the way to the right.
Yeah.
Okay? But that's not enough. So if I run this, okay, and if we look at if I say y is this and x is this, and if I do bubble sort on all it does is it moves the biggest number to the end, right? So 8 is at the end and 5 is at the end, but it didn't sort any of the other numbers because it just went through it once. So we have to run through it so that 8 ends at the end, and then we have to run through it again so that 7 ends at the end. But what do? We just have to. Well, are you saying?
Yeah, no. I guess my question was, why do you have to make it count conditions?
Oh, I guess we don't. We just. I guess it's a little bit inefficient, but you're absolutely right. I could just say I could just say like for k in 1 through length of, yeah, for 1 through j, okay? And yeah, I guess if I didn't do this, should it work? It should still work. Okay, so, okay, actually it should be, we'll call this, there's just a tiny bit of inefficiency in that it's running the whole thing, but let's see, did I mess something? I messed something up here. Okay, without even bothering to go 7, 6, 5, 4, 3, 2. Okay, let's see this. Argument is of length 0. It doesn't like it for some reason. Let's see. Okay, so here's a good opportunity to talk about troubleshooting, okay? So a lot of times, as you are coding, you will rarely get it right the first time. Okay, so what do we do if we end up in a situation where we don't know what's going on, right? It says argument is of length 0, and I'm not quite sure what I did wrong. So let's see. Okay, so a lot of times, one simple thing you can do is you just say, okay, let's print what x is, what it is at this point. Let's print x, or you can do cat. You can say cat. Let's say I is equal to I, and x is equal to, and let's print out x, and then let's put in a new line. Again, let's just see what happens when we run this. Bubble sort y. Okay, I is 1, x is this, x is 5, 4, 3, 2, 1. Argument is of length 0. I didn't like this in the first. J in. Oh, okay. Because j is equal to 1, it's going to be 1 to. So this is the problem. This is the problem. So let's try this out. Okay. So maybe this will work now. So yeah, one option is to just okay, let's see what happened here. This is not the result I wanted. So what went wrong? I started off at 1, and I is 2, 4, 5, and I is 1 again. I'm not sure what's going on. Am I doing something crazy here? Oh, okay. I see what's happening. Because so maybe if I printed j here, j equal to j into this, we would see what's going on here. So yeah, a lot of times it helps to have every single argument that you are using to be printed here. Okay. Another option is to kind of cat something. I got too many punctuation marks. J, J, X. Is that okay? Let's try this out now. Okay, so when we do this, what's happening is J starts off at, I moves up, but it goes all the way to 2 because in the beginning J is 2. So what I want to do is, let me see if we can do it. I think your suggestion is go all the way to length minus 1. So if I just did L minus 1, sorry, we're trying to code something a little bit different from. Okay, so this runs now, and it starts by kind of pushing the 5 over, and then you can kind of see the evolution here where it pushes everything over, and finally it ends up in the sort. So basically the difference here is that with every iteration it's going to go all the way to the last position. And this alternate coding where, so in the beginning, the first time I coded it, I said the first time we run it, we're going to go to the last position. The second time we run it, we go to the 7th, or second to the last. Third time we run it, we go to third to the last. Fourth time we run it, we go to the fourth to the last. Okay? And this thing, we're just saying, every time we run it, we're going to go all the way to the end and just run it a whole bunch of times. Okay? Run it once, So, there's just a tiny bit of inefficiency, but it's not so terrible, and it does seem to work here. Okay? You can just say bubble sort X here, and we could see each iteration going through with starting off with J at 2, 3, 4, 5, and 6, and then each iteration kind of climbing through. We can see how it gets sorted as such. Okay, so yeah, that's one here. That's one tip for debugging. Okay, if you ended up also something and you're just printing a whole bunch of stuff like the values of these unknown variables, that's one way to do it. Another way is there are built-in functions for understanding issues here. So if I change this to something else here, and I ran into errors here. Okay, so I get some kind of error. We can do you can go to debug, okay, in the menu, and you can create a breakpoint, right? And you can kind of create a little. You just click over here, or you go into the menu and you do toggle a breakpoint, something like this, and then you run it. And when you run it, where's this breakpoint not working? Okay. Yeah, when you click, I'm sorry, yeah, you have to click the source button. And when you click the source button, if you toggle the breakpoint, it's going to pause the code right there in the thing, and it brings up what's called a browser. And the browser allows you to explore inside that function, right? When you run a function, you've created a little environment, a little scope of values, and you can see that the environment, look, notice what has happened. Normally this says global environment up here, okay? But now that I have turned on these breakpoints and I've entered this thing called the browser, okay, and it says browse here, I'm inside the environment and I can see the values of each of these things. I can see what X evaluates to. I can see what iteration I'm on. I can see I is 1. What is the value of J? J is 2. And what is L? L is 5. And so as as things are going, I could say, okay, well, this is correct. So I can just click next, okay, and it runs through the next line of code, okay, and then we can see when I run through the next line of code, I can see, okay, now I has updated to 2, and so on and so forth, okay, and it stays, it keeps you inside that little scope environment where values are changing, and you can browse and see what's going on there. Okay, so kind of the low-tech version is to just kind of have your code print out the current values that are kind of hidden from the code. So when you run code and you have these for loops and all of that, those values of I from 1 through 100, those are all generally hidden. So the low-tech method is to, in your code, explicitly say, print out this value so I know exactly what this value is when it's doing this thing. And a lot of times that's enough and you can solve the problem. If you still can't solve the problem after you do that, you can set up breakpoints in your code, and when you source the code and it runs, the code will pause at the breakpoint and throw you into that little sandbox, and you can see the exact values of all of the different things running around there. Okay, I think that's good. I think that covered pretty much it. There's another example that I was going to do, but it's not a big deal. Work on the homework. I would say take a look at homework 2. You should be able to get started on that right away. And have a good weekend. We'll see you guys on Tuesday. So you got my email that I'm going to have office hours on Tuesdays and Thursdays, right? Okay, so we're good.